So let's talk about the black body radiation. First things first, if you have an oscillating charged particles, that a charged particle that emits electromagnetic radiation. Okay, so when you have an oscillator, okay, when you have a particle that's oscillating, it can lose energy, but when that happens, okay, so let's say you got something that oscillates, okay, so it oscillates back and forth. So if it loses energy, basically what you're saying is it won't be able to stretch out as far as it would. Okay, so that loses energy, and the frequency of the light that is produced, okay, is equal to the frequency of the oscillation. Now, if your oscillator absorbs energy, so if you have an oscillator and light comes in, so it absorbs energy from light, then it can gain energy by being able, and as a result of that oscillator gaining energy, is able to stretch out further. Okay? So all objects then, since we're all made up of charged particles, protons, electrons, the nuclei of your atoms are positive, all objects produce electromagnetic radiation. So everyone right now is glowing. You are glowing. You are producing electromagnetic radiation. Okay? Now, a black body radiator is one that absorbs all radiation and re-radiates all of that energy. Okay? So the ideal case of a black body is one where you have a cavity inside a metal block. Now, if you want to observe what's happening, okay, so inside this block you have radiation basically bouncing back and forth, okay, within the cavity. Now, if you want to observe the spectrum coming out of a black body, okay, you imagine you have a little tiny pinhole there. You take a peek, okay, and you look at the light that's inside that radiator. Okay, so it depends inside the cavity. It will depend on what the temperature of the object is, the spectrum. Okay, so how the intensity varies with for the different frequencies of light that you see that you could find inside that cavity. All right, so the classical prediction is this. Uh, the Rayleigh-Jeans equation predicts, okay, that the so-called spectral density, this is really just proportional to the intensity of the radiation. If you are going to plot the intensity of the radiation versus frequency, okay, you'll find that the analysis of this using classical mechanics will show that right here, okay, versus frequency, the intensity, spectral energy density will increase. So the intensity of the radiation increases as the square of the frequency. Okay, that's based on classical mechanics. So what that means is the higher the frequency, the more intense the radiation coming out of a black body. That means the very high frequencies like X-rays will have ultraviolet radiation. X-rays will have very high intensity. So that's a prediction. So that's why this is known as the ultraviolet catastrophe. It doesn't actually happen. If it were to happen, that's a major catastrophe because you'll all be glowing with infinite amount of radiation, and very deadly ones at that. You'll offer ultraviolet X-rays. Okay, so that is a classical prediction. So that's the anomaly about the black body radiation. New here is the frequency of the radiation. So what you're plotting here, the spectral density, that is the energy per unit volume per unit frequency. Okay, so if you were to integrate rho versus frequency, okay, from zero frequency to infinity, that area right there, okay, what would that be? So you have energy per unit volume per unit frequency. That gives you the energy per unit volume. Okay, that's called the energy density inside your cavity.
You said the higher the frequency.
The higher the frequency, okay, the more intense the radiation inside the cavity. Okay? Now, in this expression, this term right here, 8 pi nu squared over c cubed, okay, that is interpreted as the number of cavity modes per unit volume. What's a cavity mode? Well, it's a way for electromagnetic radiation to exist within the cavity. Electromagnetic wave inside the cavity is said to be a standing wave. That means at the boundaries of the cavity, the wave will approach zero. So what you have there is a standing wave. You've heard of standing waves in your physics classes, right? So the higher the frequency, it turns out from the analysis, is the higher the frequency of your radiation, the more cavity modes, the more ways you can make a standing wave with that frequency within the cavity. So that's why it's directly proportional to nu squared. Okay, now this average energy of the oscillator, okay, expression right here is just kT. It's directly proportional to the Kelvin temperature. K is Boltzmann's constant, and if you recall from freshman chemistry, Boltzmann's constant is just the gas constant divided by Avogadro's number. Okay, so that's just directly proportional to temperature. So you can see for a given temperature, okay, this is the expression for the spectrum. You have a spectrum that will just rise to infinity as frequency increases. Okay, in other words, this is saying we're all releasing an infinite amount of light, basically, light energy. So that's a problem there. What's the actual experimental spectrum? It looks like this one right here. It actually goes through a peak and then goes back down. This is versus wavelength. This is versus frequency. So if you look at this graph right here, this one right here, this is versus wavelength. Okay, so it goes to infinity at short wavelength. If you look at this graph right here, the classical prediction says it goes to infinity at high frequency. And the actual experimental spectrum is given by this curve right here and this curve right here, versus wavelength, and this one right here is versus frequency. Okay? So let's examine the actual experimental spectrum. Let's examine it more closely. There's a nice simulation at phet.colorado.edu. So let's take a look at that. Let's see, chemistry, blackbody radiation, blackbody spectrum. So here's the blackbody spectrum. Okay. So here's what the experimental spectrum looks like as a function of temperature. Okay. Right here. And so this is for 4800 Kelvin. You'll notice that the strongest light that is being produced by your black body is in the visible region. So you can see this object. It's going to be glowing because your eyes can detect the visible radiation. What happens if you go down to lower temperature? What happens to the intensity? It's less intense. Okay? And what happens to the peak wavelength, where the maximum wavelength that is producing? It shifts towards the longer wavelength. Okay, so it becomes invisible, right? It goes beyond the visible. Eventually, what happens? Let's go to about room temperature. What's room temperature? 300 Kelvin, right? So let's go down, down, down. Let's zoom in. Let's zoom in our scale here. So this is really gone down now. Let's do 300 Kelvin. Okay. See, the peak is already occurring way past 3 micrometers. Okay, so let me raise that up. Oops. See. So right here, so that's at 2000 Kelvin. So you can see it shifts to the right. Not only does it get weaker, less intense, but the peak wavelength, the wavelength where you have the peak in your emission, shifts to longer wavelength. Okay? Now, the spectrum that comes out from the sun and from a light bulb resembles that of a black body. So you can actually use the spectrum that you would record from things like the sun or a light bulb as a way to estimate the temperature. So what would be the estimated temperature of the sun then? About 5,700. What's the color that you see from the sun? It's around yellow, right? Yeah. Your eyes perceive yellow. It's really a mixture of all of these colors right here. Okay? And your light bulb? You still see some yellow from your light bulb. Okay? Not sure. That's what you perceive as the color. It's a mixture of all these wavelengths, and what your eyes will perceive would be that yellow color. All right. Now, what would be if you were the only thing that's generating light? Okay, so you're in a completely dark room in a way. What would you be able to see yourself, or would somebody be able to see? No, because at 300 Kelvin, what's the peak intensity? You can see there's very little. You generate very little visible radiation. What you generate is actually in the infrared range. Okay, and that's why if you want night vision goggles, okay, you want to see in the dark, you need an infrared detector. All right. Okay, so let's see. What happens to the overall intensity as the temperature increases? What's the answer to this question? As you heat up an object, what happens to the overall intensity? It increases. In fact, it goes up to the fourth power. Okay, so power per unit area, that's intensity, right? That's joules. Power is joules per second per unit area, so that's joules per second per square meter, or that's a watt per square meter, right? So that's directly proportional to the fourth power of the Kelvin temperature. And the proportionality constant sigma right here is 5.67 times 10 to the negative 8 watt per square meter per Kelvin to the fourth. This is known as the Stefan-Boltzmann's law. Basically what it's saying is the hotter the object, the more intense the radiation. And what happens to the peak intensity? Does it shift to longer or shorter wavelength as temperature increases? It shifts to, let's see, let's go back. As the temperature increases, it shifts to, the peak intensity shifts to the left, right? Shorter wavelength or higher frequency. So peak intensity shifts to shorter wavelength. Okay? This relationship, the lambda max, where that peak intensity occurs, okay? Where that peak intensity occurs, like at this particular temperature, lambda max would be right around here. So this wavelength right here would be your lambda max corresponding to this temperature right here. So lambda max and temperature, we say, are inversely proportional. The higher the temperature, what happens when you raise the temperature? The lower the lambda max. So just like your Boyle's law, higher pressure, lower volume, whenever the two things are inversely proportional, the product is a constant. Okay, so that relationship can be summarized by this equation right here. This is known as Wien's law. Lambda max, that's the wavelength where the maximum occurs, times the temperature is a constant, and that constant B is this value right here, 0.002898 meters Kelvin. Okay? So let's apply that to this question. Estimate the peak wavelength of radiation coming out of a person's ear. What's the typical temperature of a human body? 98.6 Fahrenheit. What would that be in Celsius? 37 degrees Celsius. So that's how much in Kelvin? To go from Celsius to Kelvin, you add 273. So 37 plus 273 is 310 Kelvin. So lambda max is equal to B over T. What's our B? 0.002898, 2898, right? Meters Kelvin over our temperature is 310 Kelvin. Kelvin cancels out. And what would that be? 0.02898 divided, by 10, that's 0.002898 divided by 310 Kelvin. That is 9.35 times 10 to the negative 6 meters. Okay? What would that be in nanometers? 1 nanometer is how many meters? 10 to the negative 9 meters, right? So that would be 9,350 nanometers. Okay, so remember your infrared, your electromagnetic spectrum, 400 to 800 is visible, right? Nanometer. So past 800 nanometers, you're beyond the red, right? This is red, the violet's over here. So that's in the infrared range. Okay. Let's see if you remember what we've covered so far. Rayleigh-Jeans equation, this is the classical prediction of what the black body radiation should be, which is wrong, right? It predicts the ultraviolet catastrophe. So it agrees with the experimental black body spectrum at short wavelengths or long wavelengths, and it fails at short or long wavelengths. So the first answer is it agrees at long wavelength and fails at short wavelengths. Okay. So if you remember versus wavelength, what would the intensity look like for the Rayleigh-Jeans equation? Goes fails at the short wavelength. It has good agreement with the experimental spectrum at, so this is good here, right? Bad at short wavelength. That's why it's called the ultraviolet catastrophe. Okay. Now, how was that anomaly, okay, the disagreement between the predictions of physics with reality, how was that resolved? Well, basically what that meant was the physics at that time that we used to make that prediction, the Rayleigh-Jeans equation is wrong, right? So if you recall, the Rayleigh-Jeans equation says that the spectral density is equal to this, right? This is the number of cavity modes per unit volume, per unit frequency, times the average energy of the oscillator. And the Rayleigh-Jeans equation says that the average energy of the oscillators would be kT. So to try to explain the blackbody spectrum, Max Planck made a very radical assumption. He made the assumption that the energy of the oscillators is quantized. Okay, what does quantized mean? It's restricted. Okay, it cannot have just any value. It's restricted to certain allowed values. It's like money is quantized. You can have 1 cent, 2 cents. You cannot have 1.1 cents. There's jumps in between, right? So according to Planck, okay, you can explain the blackbody spectrum if you assume that the energy of oscillators is quantized and proportional to the frequency. So he said it's equal to some constant h times the frequency nu, and it's a multiple of that. So n here is 1, 2, 3, 4. So it can be h nu, 2h nu, 3h nu, and so on. Okay? So that's what quantized means. For example, let's say h nu was 3 electron volts, then that means the energy can either be 3 electron volts. If it were to absorb energy, if it were to gain energy, it has to gain at least 3 to bring it up to 6. It cannot have 4. It cannot. So if it has 3 electron volts, and you gave it 1 electron volt of energy from light, it won't take it. If you give it 2 electron volts, it won't take it. If you give it 3 electron volts, it will take it up to 6. It will be able to stretch further. Okay? If you want it to be to gain some more energy, what's the next amount of energy it can have? Another 3 electron volts would bring it to 9 electron volts. So it would be a multiple of h nu. Okay? So if h nu is 2 electron volts, okay, if it were to gain energy, it has to end up at 4 or at 6 or at 8. So it has to be a multiple of h nu. Okay? If that is the case, okay, Planck was able to show that the energy of the oscillator would be the average energy of the oscillator would be equal to h nu over e to the x minus 1. So it's h nu over e to the x. X hap is defined to be h nu over kt, where kt is Boltzmann's constant minus 1. So instead of just kt here, this is no longer kt. This average energy of the oscillator is h nu over e to the h nu over kt minus 1. Okay? So this is Planck's prediction of what the blackbody radiation is. The spectrum from the blackbody is going to be if the energy of the oscillators are quantized. Okay? So let's take a look at that equation. That equation actually does agree with the experimental blackbody spectrum. Okay, let's see how that agrees, okay, with experimental data. What happens as nu approaches infinity? What did we say the spectrum looks like? It goes up and then goes back down, right? Versus frequency, right? And Rayleigh-Jean's equation, the classical prediction says it agrees at low frequency, right? But it fails at high frequency. This is versus frequency. Okay. So let's examine this expression right here. 8 pi nu squared over c cubed. Okay. What happens as frequency approaches infinity? This goes to infinity, right? So this term approaches infinity. But what about h nu over e to the x minus 1? What happens to that? This one, you have an exponential term raised to the x, but x is just h nu over kt. You have an exponential term raised to an expression involving nu. So e to the x is going to approach a very large number, right? As nu approaches infinity. So this entire expression right here is going to approach 0. So when you multiply two things, one approaching infinity, but the other one approaching 0, since this term has this thing that approaches 0 is exponential, it goes to 0 faster than this other one can go to infinity. So what ends up happening is eventually this second term wins out over here at high frequency. So the intensity goes back down to 0 eventually. And so you have that maximum. Now, what's the physical interpretation of that? Basically, what this is saying is that if you have high frequency oscillators, okay, those are the picky ones, right? They're not just going to take any amount of energy. If an oscillator has an energy of 10 electron volts, it's not going to accept 1 electron volt. It's not going to accept 2 electron volts. It needs at least 10 and then 20, right? So they're less likely to gain energy because they're going to need more energy before you can excite them. Okay, so when you say an oscillator gains energy, we say it's excited. For you to excite a high frequency oscillator, you need more energy. So they're less likely to gain energy. So they're going to contribute less to the average energy of the oscillator. Your very high frequency oscillator can emit very high frequency. There are fewer of them that can emit. There's fewer high energy. There's fewer excited oscillators that have a high frequency, right? So that means their contribution to the average energy of the oscillators would be less. Yes. Okay. If you have fewer A's in your transcript, then your average would be the A's won't contribute as much to your average, and that's another way of looking at it. Okay. So that's the physical explanation for that. Let's take a look at the limit at low frequency. What happens at we've shown that it does go to 0 at high frequency, right? What happens at low frequency? Here's your expression right here. Okay. You recall your power series expansion for e to the x is x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x squared over 2 factorial and so on. Okay, so that's it. So x to the 0 is what? 1. And what's x to the 1? What is 0 factorial? Just 1. So that's just 1 right there. X and 1 factorial is just 1. So that's the second term. The third term is x squared over 2 factorial. What is 2 factorial? That's 2 times 1, right? What's 3 factorial? 3 times 2 times 1. So that's the expression, the power series expansion for e to the x. Now, what happens as frequency approaches 0? H nu over kt is x, right? Now, so if nu approaches 0, what happens to your x? X also approaches 0, right? Correct? So, what happens with e to the x minus 1 if x becomes very small? Look at this expression right here. Yeah. The small, like if you go like x is 0.1, what would x squared be? 0.01. X cubed would be 0.001, right? But if x was like 0.0, okay, if x was like 0.01, what happens to x squared? 0.00001, and x cubed would be 0.000001. So these higher order terms tend to drop out, tend to become negligible as x becomes very small. So you can say that e to the x, okay, your e to the x approaches 1 plus x at very low values of x. So we're going to make a substitution then. As we're approaching x equals 0, this e to the x is going to approach the expression 1 plus x. But what is e to the x minus 1 then? What is 1 plus x minus 1? It's just x. Okay? So, if that's the case, our expression will then simplify. What is rho as x approaches 0? Approximately is equal to 1. 8 pi nu squared over c cubed, okay, h nu over, instead of e to the x minus 1, you're just going to have x, which is, what is x? H nu over kt, right? So instead of e to the x minus 1, you just have x. So, and so what happens? Cancel h nu, and what do you get? You have 8 pi nu squared over c cubed times kt, which is the Rayleigh-Jeans expression. So you get agreement at low frequency, you get agreement at high frequency. So we've seen that Planck's equation fits or agrees with the experimental spectrum at high frequency and at low frequency. What about in the middle, where the peak occurs? Well, let's see if we can derive Wien's law from Planck's equation. If you recall, Wien's law says that the wavelength where maximum emission occurs is inversely proportional to the Kelvin temperature. So when lambda is equal to lambda max, then you would expect the derivative of the spectral density with respect to lambda to be equal to 0. Okay, so all you have to do then is take the derivative of the spectral density with respect to lambda, set that equal to 0, and solve for the lambda where that happens. So the derivation for that you can get to from this website right here. So let me show you where that is. So you just do a search for hyperphysics, Blackbody radiation, Wien, and type the word Wien, and you should be able to get to that website right there. So Blackbody radiation concept, Wien's displacement law, and down here development of the relationship. That's where the derivation is. Okay, and so this is the step-by-step derivation. Basically, you have the expression for spectral density versus wavelength. That's per unit wavelength. Okay, it's this one right here. Take the derivative of that. Set the derivative equal to 0. You make a substitution here. Letter A is used to represent the constant hc over k. Set it equal to this. So when you set the derivative equal to 0, okay, this is what you get. And you cannot really solve for lambda in terms of t. You have an expression that looks like this, and so this has to be numerically solved. And if you did that, this is the expression you get. Lambda at the maximum intensity times the Kelvin temperature is 2.898 times 10 to the negative third meters Kelvin. Okay. So one thing you'll note is that you cannot just use the expression for spectral density versus frequency and substitute express frequency in terms of lambda. You have to multiply that by c over lambda squared. So you cannot just replace nu by c over lambda. Remember, lambda nu is equal to c, right? So let's see why that is. For example, what I meant to say there is that here, okay, you cannot just say that this is, you cannot just say that the spectral density per unit wavelength is equal to 8 pi, and then nu is c over lambda, right, over c cubed times h, and then c, nu is c over lambda over e to the h, nu is c over lambda kt minus 1. Okay, you cannot just do that. You have to have an extra term here that says c over lambda squared. Okay, so this is a spectral density per unit frequency. This is, multiply that by this expression, you get the spectral density per unit wavelength. Why is that? Well, here's a way of looking at it. You need to realize that, okay, the integral from nu1 to nu2 of rho of nu at a given temperature, integral from nu1 to nu2, that should be the same as the integral from lambda equals c over nu1 to lambda equals c over nu2, okay, of rho of lambda t d lambda, this expression right here. Okay, so if we're going to do a change in variables, our integration variables, then what we have to say, what we say then is d nu is equal to d nu d lambda times d lambda. Okay, so it's like saying d nu, d lambda cancels out, right? So what is d nu with respect to lambda? Nu is equal to c over lambda. So if you take d nu with respect to lambda, then it's like saying y equals constant over x. What is dy dx? It's going to be negative c over x squared. So this is going to be negative c over lambda squared. Okay, so d nu then is this. So let's rewrite this one right here. This is equal to integral of rho of nu t, spectral density per unit frequency, times, instead of d nu, I'm going to write d nu d lambda times d lambda. Okay, so d nu over d lambda is minus c over lambda squared. Okay, and so since I have changed my integration variable, my limits would now be in terms of lambda. So this is when lambda equals c over nu 1 to lambda equals c over nu 2. Now, let's call this lambda 1 and let's call that lambda 2. Since if nu 1 is less than nu 2, you're integrating from nu 1 to nu 2, for example. Okay, nu 1 to nu 2. If nu 1 is less than nu 2, then you know that lambda 1 is going to be greater than lambda 2. So if you want to start from the lower lambda to the higher lambda, you switch these limits. Okay, so you integrate from the lower lambda, which is going to be lambda 2, to the higher lambda, which is lambda 1. This is going to be, and if you're switching limits, then that negative sign disappears. Okay? If you switch limits of a definite integral, you get the negative of the original. So this is going to be rho of nu t c over lambda d lambda. Okay? Oops. So this expression right, c over lambda squared. Sorry about that. Nu, okay, times c over lambda squared d lambda. So this expression right here is the spectral density per unit wavelength at a given temperature. Okay, and so that's what we have up here, right here. Okay, and if you did that, what happens? Have, remember, rho of lambda t is rho of nu t times c over lambda squared. So that's going to be equal to 8 pi nu is c over lambda squared over c cubed times h nu, and nu is c over lambda, divided by e to the x, which is h nu over lambda, and nu is c over lambda, h nu over kt, and nu is c over lambda, so hc over lambda kt minus 1 times c over lambda squared. Okay, so you have, to simplify this, you get c cubed in the numerator. You have c squared and c, that cancels out, c cubed. You have 8 pi hc over, you have lambda, oh, that's lambda squared. There's another lambda, so that's lambda cubed, and there's another lambda squared, so that's lambda to the 5th, okay, times, so the h is already taken care of here, so times 1 over e to the h c over lambda kt minus 1. And that is the expression that you have in your textbook, and that's the same one that we have right here. Okay, 8 pi hc over lambda to the 5th times 1 over e to the hc over lambda kt minus 1. All right, so let's verify Planck's radiation equation, Blackbody equation, to see if it's consistent, in fact consistent with Wien's displacement law and the Stefan-Boltzmann law. Okay, so let's use Mathcad to do that. K, Boltzmann's constant is R, 8.314 joules per Kelvin per mole. So that's the gas constant R divided by Avogadro's number, 6.022 times 10 to the 23rd per mole. And let's just verify what K is. K is that which is joules per Kelvin. Okay, 1.38 times 10 to the negative 23rd joules per Kelvin. Speed of light is 2.998 times 10 raised to the power 8 meters per second. Planck's constant is 6.626 times 10 to the negative 34 joules second. And let's calculate lambda, our spectral density from lambda equals 1 nanometer up to 800 nanometers. So we'll start with 1 nanometer in steps of 1 nanometer. So 1 nanometers, 2 nanometers, semicolon, that gives, and then the final wavelength is, let's say, 800 nanometers. Okay? Okay, I need to define what a nanometer is. Nanometer equals 10 to the negative 9 meters. So now I'm going to get the spectral density, define the spectral density. Rho R control G makes it Greek. It's a function of lambda, and temperature T equals 8 times pi times h times c divided by lambda, L control G, raised to the power 5th, space bar, times 1 over e raised to the power h nu, and nu is c over lambda, h nu over kt, so kt stays here in the denominator, space bar, minus 1. Okay, so that's the spectral energy density. So this is density, this is energy per unit wavelength per unit volume. So the unit for this should be joules, okay? Joules per nanometer per meter cube. Okay, so let's graph that. I plot. I'm going to plot on my x-axis lambda in nanometers, and for my y-axis rho of lambda at 6,000 Kelvin, and my unit is joules per nanometer per meter cubed. And there's your spectrum. You can see it does go peak at around 500 nanometers, and then it drops down. And if we extend this, let's go ahead and extend this to about 2,000 nanometer. You can see it does eventually go down to 0. Okay, so that is your spectral density. So you would expect this part right here, long wavelength n, to be consistent with the classical prediction. Okay, the classical, if you recall, prediction, the Rayleigh-Jeans equation fails at short wavelength, but this Planck's equation does have the right behavior at short wavelength. It goes back down to 0. All right, let's plot at a lower temperature. Let's say at rho at half of 6,000 Kelvin, so 3,000 Kelvin. Okay, and our unit is joule per nanometer per meter cubed. And you can see that at 3,000 Kelvin, your emission is much weaker. Okay, so you would expect it to be, in fact, 16 times weaker because your temperature is cut in half. So 2 to the power 4. Remember, total energy density is directly proportional to T to the power 4th. So 2 to the 4th is 16. So let's go ahead and multiply that by 16. Okay, let's multiply this curve by 16 so it's comparable, times 16. And you can see that, in fact, the wavelength where the peak occurs has shifted to the right, and it's about double. If you look at this scale right here, you can see this peaks near 500 and this one peaks near 1,000. If you want to calculate the actual lambda max, let's say for number 1, the red curve would be 2.898 times 10 to the third meters times Kelvin divided by 6,000 Kelvin. Oops. So lambda max 1 equals 408.483 meters. Make that nanometers. Okay. Oh, that should be 10 to the negative third meters. So that's 483 nanometers. And lambda max 2, the blue curve is 2.898 times 10 to the negative third meters Kelvin. This one over 3000 Kelvin should be twice as much, and max 2 equals 966 nanometers. Okay, right around 1000 over there. Okay, so that illustrates Wien's displacement law. Let's see if Stefan Boltzmann's law is also consistent with this. If we take the integral, let's see, definite integral of rho of lambda 6000 Kelvin d lambda from integral from 0, okay, and to avoid a problem with division by 0, we're just going to integrate starting from 1. Okay, there's going to be a little bit of an error. Okay, you don't want to stop at 2000 because you really want to integrate to infinity. So let's extend this plot to 8000 nanometers. Okay, 8000, it's pretty much dead by then, both spectra. So integrating up to about 8000 nanometers would be like integrating to infinity. So from 1 nanometer to 8000 nanometers. Okay, and that's the integral right there. This is joules per meter cubed. Okay, so you'll notice it gives you a unit of Pascal because joule per meter cubed is a Pascal. But this is really energy per unit volume. Okay, so that's at 6000, and let's do the same integral. Just copy this, and this time I'm going to replace 6000 by 3000. Oops, 3000, and I get 0.061. Now I would expect this to be 16 times smaller. So if I multiply this by 16, I should get more or less the same answer as the one at 6000. And you can see 0.979, 0.972. There's a slight error here in the calculation. That's just a round-off error. Okay, so you can see that this Planck's formula is consistent with Wien's displacement law as well as the Stefan Boltzmann law. Okay. So if you want to learn more about this, it's a very nice website, Hyperphysics. You just do a search for Hyperphysics at Georgia State University, gsu.edu. Just type that, and you'll find, okay, when you get to that website, it's a really nice website if you need a review of all the physics that you've had and some that you may not have had. This is a good place to go to. Click on quantum physics, and right here, this is where discussion of the failures of classical physics. So one of those failures is the blackbody radiation. Okay, so if you click on blackbody radiation here, it gives you through a series of explanations. Okay. And here's the one that explains why the number of cavity modes is directly proportional to the square of the frequency. See, this one right here is higher frequency. There's more ways you can fit higher frequency standing wave within the cavity than you can with a lower frequency standing wave. Okay, so if you need more details about this, this is a good website to go to. The important thing to realize is that, as far as we're concerned, the most important thing to take out of this is that what? Planck had to make an assumption about quantization, about something having restricted values. There's no reason why there should be restrictions in how much energy an oscillator can gain. In fact, I believe Planck's original intent was just to introduce that that h and show that if you take the limit as h approaches 0, then you get the correct result. But he had to stop at a small number, and that constant right now, the modern value for that constant is what was the value for h? 6.63 times 10 to the negative 34 joule per second. You can see that's a very small number. Okay, so the important thing to realize, the most important takeaway from this lesson is that you're looking at a phenomenon that could not be explained by classical physics, physics that was known at the time. You have to introduce a radical assumption that energy is quantized. That was the only way to explain it. Okay? There's a couple of other videos on YouTube you might want to look at. These are more geared towards explaining blackbody radiation in layman's terms. So I strongly suggest you look at the radiation. There's one from Brightstorm right there. It's got a lot of hits. It's a very that Brightstorm channel has some really nice reviews of physics. Very quick, very short lessons on physics. Okay. Cassiopeia, blackbody radiation. Couldn't find it. Let's see if there's a better way to search for it. Just do quantum mechanics. Cassiopeia project right here. Okay, quantum mechanics chapter 1B of 6, and this one right here has a very nice description of quantum mechanics in layman's terms.